Today we start Unit 6, which is on thermochemistry. Thermochemistry is the study of energy flow during chemical reactions. That's what thermochemistry is. So that means some chemistry is going to be involved. We're going to get into reactions taking place, but we're going to shift focus from what's happening with the matter, and for a little bit we're going to focus on what's happening with the energy. To study energy, we probably should first define what energy is. This is a fairly decent working definition of energy, which is often abbreviated E, or sometimes I will say NRG for energy. Energy is the capacity. It's not a thing. It's not like matter, but it is a measurable capacity, however. It's a capacity to do work or to cause temperature change. We'll have to define what doing work actually means later on. But temperature change, we all pretty much know what that means. The thermometer rises. It gets hotter or colder. The unit of energy that we use in scientific studies is the joule. It's Joule. The abbreviation is J, and of course it's an SI unit, so we could scale it up and make kilojoules, or scale it up further and make megajoules if we wanted to. Those things will happen. It's in honor of Sir Robert Joule, who was one of the fathers of chemistry. And the basis of the unit really comes from physics. We'll get into it a little bit later on, what exactly a joule means. One of the most important things to take into consideration when you're studying energy is this law called the law of conservation of energy. And what this law states is that the total amount of energy in the universe is constant. The total amount of energy in the universe doesn't change. There's another name for this. This law is also named the first law of thermodynamics. That's why most physicists are going to refer to this law, the first law of thermodynamics. It basically says that however much energy you have, that's the maximum amount of energy you will ever have in the whole universe. Actually, energy is stored. That capacity to do work or cause a temperature change is stored in two different ways. One of them has the nickname potential energy. And I say nickname because it's really, there's only one kind of energy. This is just a way that science teachers and scientists themselves actually sort out the world a little bit and make it easier to categorize things. A better name for potential energy really is energy of position, because all the examples of potential energy that you ever read about in an introductory science book or something like that, they really have to do with where two things are with respect to each other. All examples of energy of position can be boiled down to this basic model. Think about two ends of a spring. Here are like two balls that are stuck on the ends of a spring. If I think about those two ends of the spring, there's an attraction for these two objects because of the spring. And if I take those two objects and I move them away from one another, the attraction that they have for each other stores energy. We've all done something like this. Take a slinky and you stretch it out. It takes energy to do that. You have to do work on it. And you get that energy back as soon as you let go. So these objects, if you stretch them apart, store energy in their position. So it's objects that attract that are pulled apart. That's one way that you can store energy in position. Several examples of this exist. Moving an object through a gravitational field would be one example. Let's say I take this pen and I move the pen to a higher location. I just moved it farther away from the center of the Earth. Gravity attracts this pen. The two objects, Earth and the pen, are attracted to each other. If I move the pen farther away, I've stored energy in its position. That's potential energy or energy of position. Think about magnets. If I have two magnets that are stuck to each other and I pull those magnets apart, they're attracted to one another. I separate them from each other. Well, I've just stored energy in their position. On the chemical scale, electrons and protons are attracted to each other. So if I move electrons out of an atom, for example, by ionizing it, I've stored energy in that system too. We'll come back to that idea later on. The other way that energy can be stored in position of objects is sort of the opposite. Imagine my two spheres connected by a spring. If I push the spheres toward one another, what I'm doing is I'm moving them together against the repulsion. So objects that repel each other, when they're smushed together, when they're forced together, they store energy in their position too. So you can think about the ends of the spring here as a model of that, but you can also think about two magnets. The north pole and the north pole of a magnet don't attract, they repel. So if you take the north and north pole of a magnet and you shove them together, it's hard to do. We've all done that before because energy is stored in that position. The other way that you can store energy, in other words, store the capacity to do work or cause a temperature change, is through the motion of objects. And the energy of motions of objects has the nickname kinetic energy. It's abbreviated KE very often. So as an object moves, it carries energy with it. So I'm driving my car down the road, it has a lot of energy behind it. If I hit something, I'm going to cause some damage to that thing. I'm going to do work on that thing. We can actually, it turns out, quantify how much energy is stored in the motion of an object. The kinetic energy, the energy stored in the motion of an object, is 1/2 the mass of that object in kilograms times the speed or velocity of that object in meters per second squared, and that'll come out to joules. That's a physics thing. We won't have to do that, but it is possible to actually put a number on this. In chemistry, one of the places that kinetic energy shows up most often is not in the motion of large objects, but in the motion of very, very tiny objects. The atoms and molecules and ions that everything is made of, the average kinetic energy of all those particles that are in a mixture or in a substance turns out to be directly proportional to the temperature. So you stick a thermometer in some water and you watch the fluid go up in the thermometer. You put a heat probe in some water and you watch the numbers rise. What's happening is the particles of water, the molecules of water, are vibrating more rapidly. They're jiggling around faster. And when the average kinetic energy of the particles goes up, that's what an increase in temperature is. That's what temperature measures, is the average kinetic energy of the particles. An important part of thermochemistry is something that we call thermodynamics. And thermodynamics is the study of the exchange of energy between a system and the surroundings of that system. There are three terms that we need to define that are really relevant to the study of thermodynamics. One is the system. The system is very simply just the part of the universe that you are the most interested in, the part you're studying. This might be an object, it might be a chemical reaction, that's very important in chemistry. It's just a small part of the universe, the part that you're trying to find out is energy going into it or out of it. The surroundings, well, the surroundings is the whole rest of the universe. So that's a really big space and it's hard to get a handle on it. So we have some tricks for dealing with that. And then the third term is boundary. And the boundary is a real, sometimes, or imaginary, sometimes it only exists in our mind, separation between the system and the surroundings. Now we can never know the total amount of energy that's stored in any system. It's not possible. Even if you take a very simple object like a cup of water and you can measure its temperature and you could estimate what the average kinetic energy of the particles is in there, but that cup of water is on the surface of a planet that's spinning around really fast, and that planet, in addition to spinning around, is also rotating around the sun one time a year, so that's moving really fast. And the whole solar system is hurtling through the universe at an incredibly high rate of speed. And so to get a feel for all the energy that's stored in that cup of water, it's impossible. So we don't really deal with total amounts of energy. We deal with changes in energy. That turns out to be the most important thing to study. You can exchange energy between the system and the surroundings in two different ways. One of them we call heat. Now, heat is really confusing for most people who are just beginning to study this stuff because we often get it confused with temperature. Heat and temperature are not the same thing. Changes in temperature show us that something's going on with heat, but they aren't the same thing, really. Heat is abbreviated Q. That's our symbol that we use for heat. And heat we can call the transfer of energy between two objects when that transfer is due to a temperature difference. In science, this Greek letter delta that looks like a triangle, that means change or difference almost all the time. So delta T means difference in temperature. Here are two examples. I've got on the left-hand side here a coffee cup. Obviously inside this coffee cup is something hot. Outside is air, which is cooler. Energy change through heating has to have a temperature difference in order for it to occur. And the energy always flows from the hot place, which would be the coffee here, to the cold place, which would be the air outside. And so the direction of Q, the direction of heat flow, would be from the inside of the cup to the outside. And when the coffee cools down to the point that it's the same temperature outside, there's no temperature difference anymore, and energy can no longer be exchanged through heating. On the right-hand side, I have the opposite situation. Here's a cold beer standing there. Here, it's warmer outside, and it's colder inside. And so energy is going to flow from the warm air into the beer until there's no difference between the two temperatures. The other way that energy can be exchanged between system and surroundings is through work. Work we abbreviate W. Work is defined this way: force acting over a distance. So if I take an object, like a rock, and I apply force to it, if I don't move that rock, technically, according to a physicist, I haven't done any work. I might feel after pushing for a while that I've done some work, but I haven't. Until I move that rock someplace, I haven't done any work. So this idea gives us an equation for understanding how much work there is. If I can move this rock through a distance that I'll call delta D, change in distance, well, if I applied that force F over that delta D, that's how much work got done. So work is defined as the product of force times the change in the position of an object, the force times the distance that the object moved. That comes to us complement of physics, kind of the sister science of chemistry. Now, because there are only two ways to exchange energy between a system and the surroundings, for a system, we can rewrite the first law of thermodynamics. Imagine our system here. This box is our system. Everything inside the box is the system. The surroundings is everything in the universe outside the box. The only way I can get energy out of this box is through Q, heating, or W, working. I don't even like to use the words heat and work because I think they're confusing. Heating and working are more accurate because they are really methods of changing energy. Now they have units of energy, both heat and work do, but heating and working are just methods of moving energy out of or into a system. So I can only get energy out of the system or into the system through Q or W. Here's what this means. If E is the energy of the system, then any change I experience in E can only be the result of the Q that happened, the heating, or the work that happened, the W. I can't have a change of energy that means I created some energy or destroyed any energy, because that would violate the first law of thermodynamics. So for a system, this is a restatement of the first law of thermodynamics. Any energy change that happens inside of a system can only be because there was work done or there was heat exchanged. One really important form of work that happens in chemical situations is when a gas expands, and this is called pressure volume work. Let's imagine this expanding gas. So all of these little specks inside this container here, those are gas molecules. We can imagine atoms of a gas or molecules of a gas. And here's a piston that can move. So this is sort of like the syringes that we've used before. And right now I've got these two little blocks in place that are holding that piston. I can imagine that those blocks could be pulled away. You can imagine that there's a force pushing on this object. Here's what pressure is. We've defined this earlier in the gas laws. Pressure is force divided by area. So we need force because that's what's in the work equation. So let's solve this equation for force, and here's what we find. Force is equal to pressure times area. So that's the force that we've got here pushing on this gas. Now, if I remove the blocks and allow this gas to expand, the gas will do work on the surroundings. Watch this. As the particles of gas pushed the piston out, they did work because they applied a force and they moved the piston through a distance, delta D. So the work done here, by our definition that we had earlier, is force times that delta D. But force is pressure times area, so we could substitute, and instead of force times delta D, we could say pressure times area times delta D. But this piston, when you think about it, is really a circle. It's not a looks like a rectangle here, but that's just because we're looking at it from the side. So when the circle moves to a new location, what it does is it traces out a cylinder. And if I take the area of that circle, which I could find by pi r squared, and I multiply that by the delta D, well, I've taken the base of a cylinder and multiplied by its height, really. And in geometry, we call that volume. So there's been a change in volume. Area times delta D is just a change in the volume. So work, pressure volume work, is equal to P, the pressure, times the change in volume that's experienced. Now our gas laws give us ways to deal with changes in volume, so that could be useful here. One more thing to consider. The sign on W here should be a negative number, and that's because the system, the gas we're studying inside that cylinder, lost energy as it did work. It doesn't have as much energy as it used to because it did work on the surroundings by pushing. So just verifying that the sign on W is negative when the system is losing energy to the surroundings. That's also true for Q. When energy flows out of the system, that's a negative for the system. When energy goes into the system, that's a positive for the system. Let's do this example problem. It says here a gas fills 2 liters at 2 atmospheres. When the pressure drops to 1 atmosphere, the gas expands. How much energy was lost by the gas through work? Let's model the system by drawing a picture. I'm going to imagine a cylinder arrangement, sort of like what we had in the notes. The volume, it said, originally was 2.0 liters. When the pressure on this was pushing was 2.0 atmospheres. And then the gas expands. So this has moved to some new volume, and we don't know how many liters that is, but we do know that the pressure on it is now 1 atmosphere. It's a lower pressure. So during the expansion, the pressure was 1 atmosphere. We have to calculate work here. That's what we're looking for. Work is negative P delta V. So we know what the pressure is. That's 1.0 atmospheres. That was the pressure during the change, during the expansion. What we don't know is what's the change in volume. We know the starting volume was 2 liters. We don't know the ending volume yet. However, we can find it. It's pretty easy to do because we learned in the last unit, we learned when we studied gas laws, that P1 V1 is equal to P2 times V2. So we can find that second volume. P1 times V1 over P2 is what our second volume is going to be. So we put our numbers in there. The first pressure was 2 atmospheres. The first volume was 2 liters. The second pressure was 1 atmosphere. So with atmospheres canceled out, 2 times 2 is 4, divided by 1 is 4. So that means our new volume is 4.0 liters. So our change in volume, which is what we need here, is the 4 liters that we ended up with minus the 2 liters that we started with. So that's 2 liters. So now we know our delta V is 2 liters, and we can just multiply our pressure by the change in volume, 2 liters. So the unit of work that we get is the liter atmosphere, not joules. We'll find out how to convert it later on. When I take 1 times 2, obviously I have 2, so the work done is 2 liter atmospheres. Here's a conversion factor that might be useful to you sometimes. It actually comes from our universal gas constant, R. 0.0821 liter atmospheres per mole Kelvin is one of our R's. But R can be written another way too. It can be written 8.314 joules per mole per Kelvin. So if you drop out the per mole Kelvin, which is the same in both versions of R, you get this conversion factor. 0.0821 liter atmospheres is 8.314 joules. Suppose that a system could only do pressure volume work. That was the only kind of work that the system could do. This is actually often the case in chemistry. If that were the case, the first law of thermodynamics says the change in energy is equal to Q plus W. But pressure volume work is minus P times delta V. So that means delta E, the change in energy of the system, is equal to Q minus P times delta V. So here we have another equation that in some situations might be useful to us.